We shall discuss about matrices in the reduced row echelon form. For brevity, we can write this as R, R, E, F. An M by N matrix A is said to be in reduced row echelon form if it satisfies the following conditions. First, all zero rows, if there are any, should appear at the bottom of the matrix. Second, the first non-zero entry from the left of a non-zero row is a 1, called the leading entry or the leading one of its row. Third, for each non-zero row, the leading entry appears to the right and below any leading entry in preceding rows. And finally, if a column contains a leading entry of some row, then all other entries in that column are 0. Okay? So, we say that the matrix is in the reduced row echelon form if there is a row that contains entirely of zeros, then you should find this row at the bottom of the matrix. Again, if there is a row that contains entirely of zeros, that must be found at the bottom of the matrix. All zero rows must be at the bottom. Next, the first non-zero entry from left going to right, the first non-zero entry of a row that does not contain entirely of zeros, that non-zero entry must be a 1. It's called a leading entry or a leading one of its row. Alright? So from left to right, the first non-zero entry must be a 1, and it's called a leading entry. Third, for every non-zero row, the leading entry should appear to the right and below any leading entry in preceding rows. In other words, if there are two consecutive rows that are non-zeros, then the leading entry of the second row or the succeeding row must be found to the right of the leading entry of the preceding row. Alright? And then finally, if a column contains a leading entry of a certain row, then all entries along that column must be 0. Alright? Supposing that the second row has a leading entry along the second column, so entries above and below must be 0. So let us have some examples. Say we have matrix A, 1, 0, 0, 0, 1, 0, 0, 1, 0, 1, 0, 0, 0, 0, and 0. Alright? So, the third row contains entirely of zeros. It is found at the bottom. Alright? Then, going from left to right, you see that the first entry is a 1. So this is the leading entry of the first row, while this one is the leading entry of the second row. Third, the leading entry of the second row is found to the right of the leading entry of the first row. No? Both the first and the second rows have leading entries, and the leading entry of the second row is found to the right of the leading entry of the preceding row. And finally, notice that you have the leading entry of the first row found along the first column, and the entries below are all zeros. The second column are all zeros. That's all right, because there are no leading entries. The third row, or rather the third column, contains a leading entry of the second row, and entries above and below are all zeros. Alright? So another one. 1, 0, 0, 0, -2, 0, 1, -1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, and 0. Here's another example of a matrix in the reduced four echelon form. Again, it has a row containing entirely of zeros and it's found at the bottom. All leading entries are 1. Alright? All leading entries are 1. And the leading entry of succeeding rows are to the right of the leading entries of the preceding rows. So the first row and the second row both have leading entries. The leading entry of row 2 is to the right of the leading entry of row 1. The third row has a leading entry, and it is found to the right of the leading entries of the first and the second rows. Now, how about the one here? Does it matter that it is not equal to 1? No, it doesn't matter. Why? Because there are no leading entries along this third column. Alright? There is no leading entry. The leading entry is found in the second row. But for the third column, there is no leading entry of some row. So it's perfectly alright to have a -1 here. Still, matrix B is in the reduced row echelon form. C is also in the reduced row echelon form, and it satisfies all the conditions. Still another one. Okay. This is also in the reduced row echelon form. Alright? It has a row containing entirely of zeros, but it is not always necessary that there is a row containing entirely of zeros. So it's possible that there are no row that contains entirely of zeros. Then the leading entries are all 1. The leading entries of succeeding rows are to the right of the leading entries of the preceding rows. And then, if there is a leading entry of a column, if in a column there is a leading entry of some row, then all the other entries must be 0. So these are all zeros because there is a leading entry. There is a leading entry for the second row, and these are all zeros. Leading entry for the third row, and these are all zeros. Okay? Now the negative 1 is not a leading entry. The one here is also not a leading entry. Now the following are not in the reduced row echelon form. Let us state the reason why. So supposing that we have matrix M, 1, 4, 0, 3, 0, 0, 0, 0, 0, 0, 1, negative 2. Say we have matrix N, 1, 0, 3, negative 6, 0, negative 1, 2, and 4, 0, 0, 1, and 2. Say we have matrix P, 1, 0, negative 3, 5, 0, 1, negative 2, 4, 0, 1, 3, 2. Say matrix Q, 1, 2, 3, negative 4, 0, 1, negative 1, 5, 0, 0, 1, 3, 0, 0, 0, 0. Okay. So let's start with P. Why is it that, let's start at M, matrix M. Why is it that M is not in the reduced row echelon form? We see that there is a row containing entirely of zeros, and it is found not at the bottom but at the second row. Okay? So that makes M not in the reduced row echelon form. So we say that M is not in the reduced row echelon form because it violates the first condition, that if ever there is a row containing entirely of zeros, it must be found at the bottom. Okay? How about N? It violates the second condition, that the first non-zero entry from left to right must be a 1. That is not equal to 1. So it's supposed to be a 1. So it violates the second. And also, it violates the fourth one, because this is a leading entry. That is a leading entry of the third row. So all other entries along that column, these two, must be equal to 0. And obviously they are not. Okay? So there are two conditions violated in number n. Condition 2 and condition 4. How about in P? In P, it's okay that we have 1 here, 1 and 1. These are the leading entries. But then, the leading entry of the third row is not located to the right of the leading entry of the preceding row. Do you see that? This is the leading entry of the second row. So for the succeeding row, if ever there is a leading entry, it must be located to the right. But obviously, the leading entry is not to the right, but directly below the leading entry of the second row. All right, and it also violates the fourth condition, that if there is a leading entry in a row, then all other entries along that column must be 0. So this is not equal to 0. The requirement is that if you have a leading entry in the second row along the second column, entries above and below must be 0. Then how about Q? Okay, it violates what? The fourth condition. You have a leading entry of the second row along the second column, so above, this must be 0. Okay, so it violates the fourth condition. The same thing for the entries above the leading entry of the third row. This one is a leading entry, and you see that there are non-zero entries above and below. Above, no? Above the leading entry. They are not equal to 0. Alright? So, now we know when is a matrix in the reduced row echelon form. We then state an important theorem that says that an M by N matrix is row equivalent to a unique matrix in the reduced row echelon form. Okay? What does this theorem tell us? So if you have a matrix and you perform a finite sequence of elementary row operations, you can come up with a matrix in the reduced row echelon form. Alright? So we shall perform a series of elementary row operations, to be performed on a matrix A. Alright? And then you will come up with a matrix A1 in the reduced row echelon form. Given a matrix A, we perform elementary row operations on A. And what are these elementary row operations? The first one is interchanging two rows. The second is multiplying a row by a non-zero constant or scalar. And third, adding to a row or multiple of another row. No? You perform a series of elementary row operations until you come up with a matrix in the reduced row echelon form. And that matrix in the reduced row echelon form, which we are going to label as A sub 1, is said to be row equivalent. No? Row equivalent to the given matrix A. And that matrix in the reduced row echelon form is unique. Alright? Meaning to say there is no other matrix A sub 1 in the reduced row echelon form that is row equivalent to the given matrix A. There is only one. So what we do next is we will try to work on a matrix and transform this into another matrix in the reduced row echelon form. Alright? So supposing that we are given matrix A, 2, 4, negative 2, 3, 1, and 2. negative 2, negative 3, and 1. Alright, so the idea is to transform this into another matrix in the reduced row echelon form. So find the matrix in reduced row echelon form that is row equivalent to A. Okay? So this is how we're going to do it. So let me rewrite the matrix without the bracket. 2, 4, negative 2, 3, 1, 2, negative 2, negative 3, and 1. So we start by identifying the so-called pivotal column. No? So beginning from left, going to right, identify the first non-zero column. Obviously, it is the first column. We shall call this as the pivotal column. Alright? The first non-zero. So if ever there are zeros involved, okay, if this is your matrix, the first column from left going to right that does not contain entirely of zeros, that will be your pivotal columns. In this case, it is the second column. Alright? So, along the pivotal column, we identify our pivot, the first non-zero entry. And the first non-zero entry here is a 2. And we shall call that as the pivot. Alright? The first non-zero entry. So, if you have, say, 0, 0, 0, 0, 3, 2, 1, 1, 5, 3, 8, 7, something like this, this will be our pivotal column, and 3 will be our pivot. Okay, so from top to bottom, identify the first non-zero entry, that will be your pivot. The idea is to change the pivot into a 1. And how do we do that? By multiplying the first row by 1/2. Alright? We multiply row 1 by 1/2. And the result is returned back to row 1. Okay? So we multiply the first row by 1/2. It is one of the elementary row operations, right? Multiplying a row by a non-zero constant. So 2 times 1/2, that will be 1. We use the same color, 1. 4 times 1/2, that will be 2. Negative 2 times 1/2 is negative 1. Alright? So this is now our leading entry. That is our leading entry of the first row. Okay? So if that is a leading entry, along the first column, entries below must be 0. Okay, so in this case, we need to turn this entry 3 into a 0, and the other entry negative 2 should also be turned into a 0. So what elementary row operation are we going to do with row 1? So that 3 in the second row, the element below the leading entry of the first row will become 0. Okay, so what we do is we multiply row 1 by negative 3. Okay, and then we add it to row 2. And the result is written in row 2. Okay, again, since this one is a leading entry of the first row along the first column, entries below the first column must be 0. So we need to change 3 and negative 2 to 0. And to do that, we perform an elementary row operation. We multiply a row, which is row 1, by negative 3, and add it to row 2. So 1 times negative 3 plus 3, of course, will become 0. 2 times negative 3 is negative 6, plus 1 is negative 5. Negative 1 times negative 3 is positive 3, plus 2, that will also be 5. Okay? So how about negative 2? For negative 2 to turn into a 0, we multiply row 1 again by positive 2 and add it to row 3, and the result written back in row 3. So 1 times 2 is 2 minus 2 is of course 0. 2 times 2 is 4 minus 3 is 1. Negative 1 times 2 is negative 2 plus 1 is negative 1. Alright. So next, we disregard first our first row. Consider the second and the third rows. Once again, we identify our pivotal column. The first non-zero column from left to right is negative 5, 1. Alright, so that is our new pivotal column. New pivotal column. And our new pivot is negative 5. But we are going to change negative 5 into a 1. And instead of doing that, why don't we just interchange rows 2 and 3? Let us interchange rows 2 and 3 so that our pivot will already be 1. Okay, so 0, 1, negative 1, 0, negative 5, 5, 1, 2, negative 1. We're just copying row 1. So our pivot now is already a leading entry. That is already a leading entry. It is now a leading entry. Okay, so being a leading entry, we just copy row 2. Since the leading entry is along the second column, entries above and below, these entries must turn into 0. Alright? So again, we perform an elementary row operation to row 2. We multiply row 2 by negative 2 in order to make the entry above 0. Okay? So we multiply row 2 by negative 2 and add it to row 1. And the result written back in row 1. Okay? So negative 2 times 0 is 0 plus 1 is of course 1. So the leading entry of the first row is unchanged. 1 times negative 2 is negative 2 plus 2 is 0. Negative 1 times negative 2 is positive 2. Minus 1 is positive 1. Then we turn negative 5, the element below the leading entry of the second row. We turn this into a 0. What do? We multiply row 2 by positive 5 and add it to row 3. The result back to row 3. So 0 times 5 is 0 plus 0 is still 0. 1 times 5 is 5 minus 5 is 0. Negative 1 times 5 is positive. Negative 5 plus 5 is 0. At this point, now we observe that our matrix is already in the reduced row echelon form. Okay, so we say the matrix in the reduced row echelon form, that is row equivalent to A, is 1, 0, 1, 0, 1, negative 1, 0, 0, 0. Okay,